like at least to find the steady state for this model called zero range process. That's what I was trying. In the meantime, what I was discussing is this generating function, okay, so which we will use there, okay. So now let me continue little bit on the generating function. So right, so I start with this one, like I'm just generally discuss the generating functions, and the same thing I will use there, and this concept is repeatedly used in statistical physics in many times in this class, and not in this class, in this whole series. Many times you have seen it, but it's a very general concept, and I just wanted to introduce it some way. So let us say that fn plus 2 equal to fn plus 1 plus fn. Okay, so that's a Fibonacci sequence, right? That's the relation. So now, do you know, right? I asked you to try the generating function. Anybody got that? So if you define gz equal to summation over n equal to 0 to infinity fn z to the power n, okay. So of course, so this is the one. Then fn by definition, fn equal to just z to the power n coefficient of gz, okay, in the series expansion of gz. That's the notation, okay. So you expand this function in the Taylor series about z equal to 0, and you just pick up the coefficient of z to the power n. That is pretty obvious, right? This is the expansion in z to the power n around z equal to 0, okay. So the way to find it, as you say, that one method is just dn by d z to the power n 1 by n factorial gz at z equal to 0. So if you do that, that's one way to find the coefficient, okay. And there are other methods also. I just say that this is equal to some contour integral 1 by 2 pi I. If you do not know this at this stage, you just stick to this formula. That's also fine. Contour integral, this is gz divided by z to the power n plus 1 dz, okay. So that is another way of finding this. Okay, so did you find it? Can you tell me for this one what is gz? Okay, so anyway, this recursion would not work unless you give you a boundary condition. And how many boundary conditions you need? Pick 2, right? So let's say that f0 and f1 is given. F0 and f1 are given. Okay. So f0 equal to maybe 0 and 1, or you can call it 1 and 1. So you can recursively generate rest of the 1. Okay. So now, did you find a solution to this problem? Anybody tried? Anybody tried? Nobody? No, I'm just saying that, did you find what is gz? Oh, no, you did not have time. Okay, anyway, so let me just do that. My definition is just this. So what I just multiply here, you just multiply z to the power n here, z to the power n here, z to the power n here, and make a sum n equal to 0 to infinity. Okay. Okay. So now, if you do that, this is directly, this equation becomes, this one becomes gz, of course, the last one. And what is this one? So you can call it, put just a 1 here, then so you can put a 1 here and plus 1 here and put a z here, right? That just divides, and n equal to 0 to infinity means this is n equal to 1 to infinity. So you plus f0, if you put plus f0 and minus f0, right? So if you plus f0, then this one is just gz, okay? So this is gz minus f0, okay? So this is 1 by z times gz minus f0, f0 is 0, so this is just gz, okay? Right hand side is just that. And what will be this? Can you quickly tell me now? So z to the power n plus 2, so 1 by z square. So we have 1 by z square, and then z to the power n fn plus 2 this. So this starts from 2. So the first term and the 0th term you have to subtract. So this is gz minus, first term is 0, Second term is just f1 z, z f1, z. Okay. Second term is just n equal to 1, n equal to 0. So this is 2. Is correct, na? Minus or plus? Correct. Okay. So now from this equation you can just solve what is gz. Okay. So you just write this expression. Okay. So z square, I take it here. So this becomes z and this becomes z square. So again z goes here. This z goes here. I put z here. So gz equal to 1 divided by 1 minus z 2z. No, 1 minus z. No, this z term should not be there. No, I mean, I am making. Slow. Okay. Okay. So this one, the last term is clear. This is gz. Okay. We write it again. This one, let us do n equal to 0 to 1. So the first term is just f1 z to the power 1 like that, and then other terms are there. So in this case, if I just put f0, z to the power 0 is 1, and just minus f0, then this one will be just gz, and this is minus f0 is just 0. So gz minus 0. So this is just gz. Okay. So this is just gz minus f0 is gone, but gz by z, this z is there. Okay. Gz by z plus this. So now this term starts with f2 n equal to 0. This is f2 z square. Okay. Plus other terms are anyway there. Okay. So now I have to say that z f1 and f0. If I do that, this one will be my gz, but then I have to subtract that part because which I added. So this is f0 is 0 minus z f1, minus z f1 is 1. Okay. And this one is gz minus z. So this is 1 by z square into gz minus z equal to that. So now this is just as algebra, just try to find out what is gz. Okay. So gz equal to, so gz by z square, and this is 1 by z. Okay. So now this one I will take to the other side. So this is 1 by z whole divided by 1 by z square, 1 by z square. I mean, no, you can do whatever, 1 by z square. 1 by z plus 1 minus 1 by z square. Okay. So this is gz, and you can simplify this further. Okay. No, this minus has gone, 1 by z, and this is fine. 1 by z square I have taken. Oh, minus, there is a minus sign. Okay, it's a minus sign. Okay. So this is your function. Okay. So now, given this as a function, of course you can make a Taylor's expansion, right? I mean, you can differentiate it as many times you want, and whatever you can calculate what is fn. Okay. So from this you can calculate this. So the point, you can calculate it details. I'm not going into further details. All I'm saying is that even if the point is that it appears like all you wanted to know is that to calculate fn. Okay. But somehow without knowing fn, you could calculate this sum gz, and to get fn you have this nice formula, just Taylor's expansion and this, and you can get this. Okay. So you don't need to know fn to calculate gz. Okay. That's a simple thing. Okay. So now I will just use this as a this method will keep in mind, and I will use it in different places. Okay. So this is the method. Okay. So gz equal to this. So if you want to calculate fn, this is just a mathematical trick, and at this stage it's just math. Okay. There is no start make here. Okay. And z is just some variable. You don't need to know what that variable. There is no name to it. This z is somehow, you need to know that gz exists. Otherwise, how do you write? If you're going to use this method, you need to know what gz is, right? To calculate that this function should exist. So that might put some restriction on z. Otherwise, right? That's all. Okay. So now let me go to. So what was our problem? Like we have this zero range process, and we have the number of particles which is conserved, total number of particles which is conserved. Okay. So now let me think what we want to calculate is just Qn, and which you do not know. In general, like, you know, if you want to write a generating function of Qn, that will be just Qn z to the power n and summation over n equal to 0 to infinity, and this equal to, you call it some gz. That's the same this is generating function. That's your generating function, and with a motif like this one, that Qn again given by this formula. So Qn, you know, this formula just tells you that this is just z to the power n coefficient of gz. That's all. Okay. Right. So if you some way, if you can calculate, and you know, whatever you do, right, I mean, that's the same way, you know, some way if you can calculate gz, then you can find it. Okay. So now I will have a different, this is one way of doing it. Okay. So let us see that what we are doing here and try to interpret this little bit. Okay. Then you see how this ensembles, different ensembles comes about. Okay. So Qn, this, now when you are writing a function of Qn, of course n is a conserved quantity. Okay, some conserved, something which is conserved, and that's the reason why you are doing this, because you could not do the sum with this restriction. The sum actually, right, I mean, in the partition sum, you have this restrictions, and you want to lift that restriction. So now let us see that, you know, if you take all configurations, like, you know, whatever model, like the zero range process, so you have a lot of boxes, you are putting particles. How many particles you put, it is your choice, right? And once you put, the dynamics will not change that number. So the number of particles can be anything. It can be, you know, 300 or 302 or 301 or anything. It can be any number. And once you are here, there are many configurations in the configuration space which is the same number of particles. And right, I mean, once you are here, if you start here, you will leave in this space. Okay, so that's what you are doing. So now let us see that what we did here. What is the what we do here, right? I mean, in this sum, what did we do? Okay, so let us see that some Qn. I don't bother about what exactly is the function Qn. I do not know. So what I do here, that you have for Qn versus n. Let us say that some function is there, like, you know, something like that. I don't know what the function is. Any function. Okay. So this is the Qn functions, and what I am doing is that each point n I am multiplying by z to the power n. Okay, and z, you know, for the convergence, generally it is, you know, this equation will have some radius of convergence, and, you know, some radius of convergence I always reset it to be 1. Okay, that I am free to do. Okay, so the radius of convergence of this I am setting it to be 1. If it is right, I mean, you know, at some point later I will show you that this resetting is okay. Okay. So that is not a problem. So there is no scale, so I can put it 1. Okay. So z is less than 1. So what you are doing is that for n equal to 1, you are multiplying this function by a number which is just 1. Okay, something less than 1. But if you put 2, it goes down. So this one you are pulling it down. N equal to 1, 0 is not pulled down. This one is pulled down little bit. This one is pulled out even bigger. This one is pulled down even bigger. This one is pulled down even bigger. Okay. So each of the point you are pulling it down. So basically what happens is that this function will, the new function, right, I mean, this Qn z to the power n. So this is my Qn, and this is Qn z to the power n. Okay, z to the Qn z to the power n. Okay, so that's the function. So now if you are doing a sum, it's like doing this integral. Okay, so that's what you are doing. So now it is very important to know that if you increase, so this is 1 z, let us say z equal to 0.1. Let us say you increase z, let us say 0.2. If you increase z, so what will happen to this function? It will be on the top of it or below it? On the top of it, because it will be decreased but little lower. So if you decrease, so if you increase z, then this function will be something like that. No, exponentially, but it will go down like that. Okay. So now, so right, I mean, this is your Qn. Okay. So this is like, this was Qn by z, somewhere was a probability. Okay. So now nQn, if you want to integrate in this zone versus nQn, if you are integrating in this zone, n is an increasing function, of course, this is positive. So this will be larger, right? Right. So nQn, effectively, if you think the nQn is a function averaged over this z or something, so that will be n average. Generally, n average will, as a function of z, will be an increasing function, and z equal to 0, it will be 0, because this area will be 0, because this is just everything goes down to 0, there is no area. So basically z equal to 0. So n average at z equal to 0 has to be 0, true, and Z has a radius of convergence, whatever it is, I am just setting it to be 1, because I know until now there was no scale. I am putting first time a scale, I can put it anything I like, right? I am putting it 1. So it starts with 0 and it's an increasing function. You can draw an increasing function, okay? So it's an increasing function. Well, if n average, so that's the point, Z average. So until now, you see, until now Z was something, right, I mean, just a mathematical trick. You don't need a Z. All you wanted is that you find a coefficient of Z to the power n in the series expansion of Gz. That's what you wanted, okay? So now I'm just trying to interpret this, okay? So what could be an interpretation of Z, okay? So all I'm saying is that if you are doing this kind of sum, and then if you try to calculate as a probability like nqn summation over n, call it n average, that n average will depend on Z, because you introduce a Z. Now whatever you calculate will depend on Z, okay? So you are taking the n average as a function of Z. So the first one, the mean, you are taking as a function of Z, okay? So now you can think, so now look at that. So when you are making a sum, so this one 302, so this is Z to the power 302, and you reduce it, you put a factor here. Here you put a different factor. So now this sum tells you that the conservation is not there, because you are making a sum of all configurations. You are in the whole phase space, all phase space, but different part of the phase space you are making a sum with different weights, okay? And the weight is smaller if you go larger and larger n, okay? So n is a very general name here. N can be E, n can be magnetization, n can be anything, whatever is conserved, okay? So all you are saying, the larger and larger n, the contribution of those will be smaller and smaller, okay? So now, if you are taking all configurations, of course n is not conserved, but there will be some average, right? I mean, now it's not a conserved thing, right? So this one can be interpreted as system where n is not conserved. But when n is not conserved, what is, I mean, there is an average, okay? N is not conserved, but there is average n, okay? So in this kind of system, it's not one sector, you are not in one sector, it's not like En. You can interpret this Gz is a new partition function for the system, right? It's not a non-conserved system, but then the conservation, you are exploring all the phase space, right? All n is now explored and with a different weights, okay? So if you do that, the conservation is broken, you are actually exploring all phase space, but the average of the number will now depend on Z, okay? So average will depend on Z. I'm not filling this up. N average will depend on Z. N average you can call it like, your system size is always fixed, Qn L. I'm not touching L, so I can always also divide by L, and I can call it also rho. Rho is also a function of Z, okay? The density of a system will be a function of Z. So now, so this is a ad hoc way of going, right? I mean, I do not know what Z I want, right? I mean, so now question that although things are scattered, I can ask a question. Let us say that I want to fix the average density or average number, this density to some number. Let us say I want to fix this one to 1.3, okay? Some density. If I want that, I can see that I put a number here 1.3, then I get some Z, okay? So now question is that if you are right, you want the total, suppose total this volume is some way 1000, so this is 0.3. So let us say that you want density. So you can, one thing is the canonical ensemble where exactly in this sector you move. This is canonical, okay? This is 300 and the density rho is 0.3. So this is, let us say 0.3, okay? This is 0.3. So it is, you are here. But now you are giving a different interpretation. What you are saying is that you are allow the system to go wherever it likes, but you are putting a weight now, Z to the power weight. So now I'm saying that you can get, now it is not conserved, but you get an average which is 0.3 by fixing a Z, some number, this number, right? So this system, you allow it to go wherever it likes. Now this one corresponds to wherever you go, everywhere you go with different weights, but choosing a suitable Z can give you a density which is 0.3, right? I mean, so that is something which you wanted, okay? So a conserved system with density 0.3, fixed density 0.3, and this one you can get a non-conserved system with varying number of particles, but the density, average density is still 0.3. These are the two different things. Okay, these two things are right, equivalent. Okay, that's the equivalent principle. Okay, so a non-conserved system. In a non-conserved system, you have a Z, and you have to fix Z to some value to get what you desire. So if you want to describe a conserved system of density 0.3, you go to this curve 0.3 and use this Z. You want a different density, you put some other Z. That's the way you do. Okay, and so this part is clear, right?
They're equivalent when this n is sufficiently.
They're equivalent when n is okay. Yeah. So basically, what is? Let me just if there is a question, let me ask. So now, in this system, the number of particles when the system evolves, it fluctuates. So it has a distribution, right? The number of particles you see in the system at different times will have this distribution. So is some distributions. Usually something like that. So now this one is just n average. The mean is somewhere here, and one can prove that around this distribution it is also Gaussian. Like at least this part is Gaussian. Okay. So the tail I do not know. This will be still Gaussian. So the mean is just this, but there is a fluctuation. There is also a fluctuation here. Okay. And this fluctuation depends on 1 by square root of volume. Okay, so the number of particles, if the number of the system is large, then only this one will become very thin. So the width become very small. So the width, this one is proportional to 1 by if the system is whatever this n equal to 0 to, there are many, here it is not there, but there is a volume. This is proportional to 1 by volume in a system you are working, like here. Okay, so then when volume goes to infinity, then this curve actually become like that. Okay, so it's like you want a conserved system is basically somewhere you want to make the number exactly something you want. Okay, in the other one you allow it to move wherever it wants, but it is if you pick a suitable Z, it will remain there, and if the volume is very large, it will more or less remain there. It will not fluctuate anything. So that's the equivalence. Okay. So now it is not only that. You said that this is the number of you only broke one conservation, and these two things you are making equivalent, right? So equivalence will work if all other quantities which you measure in this ensemble and the other ensemble will also match. Once you fix this, you should not have any other thing to say. Okay, that's the equivalence principle. So any other observable, now you measure in the canonical one. So observable in this fixed n. Okay, so that is equivalent. So this is O tilde in the this ensemble, which is a non-conserved n. So this is, let us call conserved. This is non-conserved, O non-conserved with a fixed n by L. So this is with a Z. Okay, any observable. So once you suitably choose this Z, this rho corresponds to Z, which you get it from this equation. Once you fix it, all other observables will actually behave, will be same in the thermodynamic limit. Okay, so that's the equivalence principle. So
this is an assumption, or
no, this can be proven. Like as I say, that fluctuations are if it's really small, the fluctuations. So this is more or less you are here. There is nothing. There is no fluctuation. N goes to infinity. That's the way. Right, so it's not that, okay. So that's the ensemble equivalence. Mostly it holds. You may construct pathological or some examples where it may violate. Okay, so you can construct examples where it violate. Mostly it is true. It's, okay. 1 by root v. Sorry, all the time I said 1 by square root of v, but when I wrote. 1 by square root of v. So this goes as 1 by square root of v. Okay, so that's the ensemble equivalent. So the point to make is that here it is conserved, which means in your when you make a sum, partition sum of all configuration, you have to bother about some constraint. But you can lift the constraint by using this kind of method. Doesn't matter what is the conservation law, whatever the law. Okay. Once you do that, you can actually interpret this. So this part is a physics part, right? This is not a method. Z doesn't have an interpretation in the generative function. Here you interpret it. Okay. So now let us see that what are the possible difficulties. What kind of difficulty you might have. So you see, rho is a function of Z. As I say that Z equal to 0, it has to be 0. That's the point. Okay. And here you have L boxes, but number of particles, because each side can take each side can take many particles, you can put as many as you want. So the density can be anything you want, okay. So this exists, right, for every, so all the points, any density, there must be, if the corresponding hold, for every density there must be a Z, right, I mean that's what you want, if the ensemble equivalence to hold. But now Z is from 0 to 1, so this curve I have not ended, so the curve must go all the way, the curve must go all the way to like this, it must diverge here. Okay, so that general principle is that it should diverge at Z equal to 1, so that if you choose this, you have a Z. Wherever you put your rho, you have a Z. Okay, so if this is the situation, here infinity is a blessing, right? I mean, so basically, if you get infinity, you are in a good shape. Okay, so now because for every density, doesn't matter what density you want, you have an equivalent non-conserved ensemble. That's a good, and because the calculations are much easier in the non-conserved one. Okay. But now,
cannot be interpreted as probability.
No, Qn, not Qn. So you can now, we'll go there. What you should interpret as a probability? Qn Z to the power n divided by Gz can be interpreted as probability, because you just divide it here, it's 1. That's a probability. Okay. So your probability can be interpreted Z to the power n Qn Gz. Okay. And we'll come there. But now let us see that the shortfalls of this prescription. Prescriptions. Okay, so now there can be situations, I don't know when, how, we will discuss and we'll come back to that, but there can be situations that the curve goes like that, and let us say it hits here, it ends here. Okay. Then the prescription fails, of course, because until this density, let us call it wherever it go here, you call it rho star. Up to this density there is equivalence. After that, these densities do not have any corresponding Z. Okay.
This sounds exactly like these.
This is why I'm talking about BC only. Yeah. So basically that's the point, right? So if the curve hits here, rho Z goes to 1. If this is finite, then you will have that finite value is called rho star. So I'm just saying that rho Z, okay, limit Z goes to 1. Actually, I could have put rho 1, but I mean better to write limit because I don't know how it hits. So this equal to rho star, okay, is less than infinity. If this is the case, right, it is some finite number, then there is no you cannot have these densities do not have a non-conserved description. Okay. The non-conserved description, when you talk about non-conserved description, it is a macroscopic description, right? So basically, those kind of densities, if you have density here, you start with some density rho, whatever your choice, your density of rho. In a system, you put whatever particles you want, you have some density rho. Okay, that's your choice. So this density, once you have this density, if it is above that, then you know that this kind of density cannot be macroscopic density. It is not possible to have a macroscopic density, like that. So now, no. Let me explain it little better. So question is that when you are here, right? So when you rho equal to this, now think of a system, actual system. So when you say that this, then any part of the system here, if you look at that, the density will be this rho, right? I mean, once you fix Z, now they're fluctuating, but average here, average everywhere will be rho. So I'm just saying that if your rho is here in this situation, then this kind of density you will not find anywhere. Okay. What you can find is that maximum whatever is possible, right? Rho star, that is possible, you get it everywhere, but that's a macroscopic density. But then you still have, so the macroscopic density can at most be, so if this is the situation, then the macroscopic density, can at most be rho star. This is the macro density. Okay, macroscopic density everywhere. So if you look at a part of the system, if you find the density cannot be more than rho star. Okay, so if that is the case, and if you have a density rho, then it's very bad. No, I mean everywhere in the system the density is rho. How is it possible that if everywhere it is rho star, how is it possible the whole system has a density rho if it is conserved? Okay, so then what will happen, that rho minus rho star times whatever the volume here, that many particles are extra and they cannot occupy microscopically. They cannot be distributed macroscopically anywhere. Okay, you cannot put everywhere. You cannot arrange them everywhere. So these particles will go somewhere. Okay, somewhere. Okay, okay. In this case, until now it is somewhere. Okay, in BC there is a difference. It will go to the lower one, but here it is somewhere. I do not know where, but it will go somewhere. Okay, so the extra number of particles, rho minus rho star time V, is the extra number of particles, and they will form a condensate. Okay, so this is, you can see the macroscopic number of particles going into some site. Okay, so what, right? I mean, so I'll pause for a system. So the condensation or whatever condensation is a phenomena when you are, it's a shortfall of this. So if rho z goes to the maximum value, if this is finite, then you have to have some particles, will accumulate, some site, some, macroscopic site. Macroscopic number of particles will occupy some site. Okay, so that.
That it has to be just on one side.
No, not yeah. It could be sublinear in one. Yeah. Yeah. It can be anything sublinear in one. So I'm just saying that so the total number of particles in the condensate will be this. How the particles will be distributed, you do not know, but it cannot be distributed everywhere. It has to be sublinear, right? I mean, if you have system size 100, if this many particles are distributed in 4, then if you take 10,000, it will not be 4,000, right? I mean, it will not, right? I mean, it will not be 4,000. It will be lesser than that. Okay. So if you take a system size 1 goes to infinity, this fraction will go to 0. The number of sites where the condensate resides divided by the number of sites in the system, limit L goes to infinity, that goes to 0. I mean, that's the, so basically somewhere. Yeah. So that is kind of, I'm talking of only the steady state. So, okay, so if you look at, in the yeah.
Time scale may
Yeah.
Exponential, it could be exponentially large. For some time it will be here, and then it could move there.
Yeah.
So this is still in the steady state.
This is in the steady state. Yeah. Because it's not that one place you have, because the system is homogeneous. No site is special, right? I mean, So basically, if the condensate can form here, there is no reason why it cannot form here. So slowly this condensate will leak out and it will create somewhere else, and this will leak out, create somewhere else, and this will kind of, it's a large body making some diffusion somewhere, and there are particles all around. So it's a big one which is also moving around. Okay, so that will be the scenario. Okay, so all this exercise, first thing what we learned is that for any conserved quantity, you have a non-conserved description. Okay, so now let us look at, just for fun. So Qn, let us call it that, you have a Hamiltonian and this is the equilibrium system. In that case, this would be e to the power minus beta h. Okay, so if you call z is less than 1, so e to the power minus beta mu. Right, I mean, because z is something you do not know, and beta is something which is already given here. So mu and z are the same variable, right? I mean, it's just tell me mu, I can tell you z. Tell me z, I can tell you mu, right? I mean, they're equivalent. So if you write that, then you can see that z to the power n is beta mu n. So basically, all you are writing is that this minus mu h minus mu n. Okay. Plus beta. And now it's okay. Yeah. So h minus mu n. So that's the, now it depends how you define. So minus mu n. Okay. So that's the way that when you want the particle conservation is broken, then you have a chemical potential coming in, and that chemical potential is coming in because of this z. Okay, what you call fugacity. So right, I mean, Arnav has already introduced there. This is the same z which I call the fugacity there. Okay. So now this is one thing, and this is true for any conserved systems and equilibrium, non-equilibrium. This is just, so basically that canonical partition function is just a generating function of microcanonical partition function. Okay. Similarly, grand canonical partition is also a generating function of the other one. So this is just a generating function you are writing, and that's the generic name is generating. Specific name is canonical, microcanonical, or whatever. Okay, the second thing we learned is that in this kind of scene, okay, so now radius of convergence, okay, let us write that. So if n equal to 0 to infinity, z to the power n Qn, Or let us say look at this equation. So if n allows values from 0 to infinity, okay, then you have to bother about the radius of convergence, right? If it is not infinity and it doesn't matter how large, but finite, then you don't have to bother. Z can take any value, okay? So now let us think of n to be energy. So if n is energy, then energy, because it has a dynamic part, velocity part, what kinetic, it's a kinetic energy and a potential energy, and kinetic energy doesn't have a limit, okay? If you have a kinetic energy, you don't have a limit. So that one is always infinity, 0 to infinity, okay? So then that restricts z to be less than 1. So z has to be less than 1. So if you call z is e to the power minus alpha, alpha has to be greater than 1, okay? That alpha is something you call temperature inverse, right? And that's the way for energy, the corresponding chemical potential is the temperature, okay, here, and the temperature has to be larger than 1, okay? Similarly for bosons, the same thing. You have n to infinity, okay? It can be any number of particles. So if you have infinity, you don't have a problem. You have a problem in the sense that you have a radius of convergence. Z is restricted. And if you remember in on-off talk, right? The chemical potential was bounded in one side. This side or that side, it depends on how you define mu, one-sided, okay? But for fermions, it is not needed, okay? So they all come together. So why condensation can happen in bosons? Because of this, because the sum is infinity. This also tells you that temperature has to be a positive, it's a number. So now let us say some situations you restrict this energy to be finite. You have some E max, okay? So in spin systems, sometimes you can do that, okay? Because you don't have a kinetic degrees of freedom, you freeze the spins into some way. So the energy can at most take some values. It doesn't have, So in this situation, then the temperature can be anything. It can be negative even, okay? And this has been seen experimentally also. If you remember the reference, it's there in Huang. It's again there in Huang. But along with the experiment, negative temperature and this, how the negative temperature come into picture. So only when you restrict the energy, this limit.
Inverse population, right?
Yeah. So, but it's there. The reference I cannot give you. But only thing is that what you have is that temperature is usually entropy, right? Del S by del E. So that can go. If you have this energy is finite, you can have a curvature like that, and then here, beta is 0, temperature is infinity, after that beta becomes negative because it's a slope, the slope becomes negative. You can have this. So I'll look at. It's not a physical temperature.
It's just temperature in terms of defining it as a
Del S by del E. Yeah. Del S by del E. Yeah. Actually, I do not. There is no right. There is no. I don't know how exactly to right. We know we experience there is a physical temperature, but I do not know what exactly is the physical temperature.
physical temperature is the temperature of the bath that you keep the system in contact with. That's it.
No, I know only a physical temperature only with some measurement, with respect to some measurement, right? Thermometer. Yeah. But then you have to put.
So thermometer meaning that you are bringing another system to come to equilibrium with this, and that will always be positive.
But the thermometer can be small with respect to its spin system.
Yeah, that's right.
Then it's not a thermometer.
No. Okay, we will not go there. We will come back to this. This is okay. No, it's true. No, but the way we understand temperature is only that. Like through this, what you call the one. The degrees of temperature is the one. I don't think there is any better definition of temperature here. So the temperature is the one which tunes the average energy, right? That's a bath, of course. Mean energy. If you change it, the mean energy of the system will change. That's the meaning. I don't know what else. Okay. Anyway, so second thing we learn is that a situation where rho z. This can happen only when this infinity, like number of particles. Like our situation, it can happen because each box can contain any number of particles. So rho z goes to 1 if this is finite. You have to check that. If you find that it is, if you find this, then there is a condensation. Okay. So in zero range process, we are going to do that. Okay. Questions until then? until now, not then. Okay. So we are discussing this zero range process. Okay, and we have these boxes. There are many boxes. So this is box number I equal to L. This is some box I, and the number of particles here is Ni, and particles can come from the neighboring, from here to the neighboring box with rate which depends on U of Ni. Okay, so this is the dynamics, and you have a periodic boundary condition also. And U of n, something which we do not know. U of n, we choose whatever we choose. We don't specify at this stage. You choose whatever you choose. But what is a reasonable functions we know, right? I mean, we can choose them for better results. But anything we can solve. Okay. So what we do, and there are many particles here. So there are Ni particles here. So after this, we just make we just made answers that the probability of a configuration Ni, this goes as, okay, I'll write equal to 1 divided by Qn. L I drop because anyway L is same everywhere. I'm not changing L anyway. I will not carry that index. So this, and then this one is just f of n1, f of n2, f of n3, that I can write it product over I equal to 1 to L. This is f of Ni. F of Ni. Okay, and then for the number conservation, I put a delta function. So this is just a delta function I put with summation over I Ni minus n. Okay, so this is my partition function, and so this is my probability. This is my answers. I do not know whether it works, but I just write it like that. Okay. So now, so whether, right, I mean, answers is something you try. If it works, it is fine. Otherwise, you just throw it, right? I mean, so let us see. I also introduce a pairwise balance. Okay, so what we try to do is that use this as answers and use pairwise balance. In pairwise balance, you have to construct for every configuration. For every transition C to C prime, you have to find suitably some C double prime which balances that, so that you have to suitably found. Okay, so we'll do that. Okay, so with this we try to see if we can find an answer to this question. Okay, so right, can I find f? F is something which you do not know, right? So what we do is that for a general configuration, it's just like whatever this is. I will not carry index. So this is, I'm just writing I. Let me write I plus 1, I minus 1. Okay, so this is, I call it K L. So K N M. Okay, the number of particles Ni minus 1 equal to K, Ni equal to N. I'm writing it like that because I don't want to carry the index, and it's like that. So 3 consecutive sites you have somewhere, right? I mean, so everything is here, but I'm not writing, just K this. Okay, so this is a general configuration. So now a change in configuration occurs because a transition of one particle goes from here to here, right? I mean, some transition. Wherever the particle leaves, I am taking that as a configuration, and C going to C prime. C prime is basically K n minus 1 m plus 1. Okay.
What you written IC? I subscript C? No. I minus 1 and then?
I plus 1.
No. What's there in the middle?
I. These are sites. Some site, whatever the site, some site where the particle transition basically you take a particle, put it somewhere else. Okay, I'm assuming that the departure site had n particles, and the neighboring site says k and m particles, and with that I'm naming it I. Okay, so n minus 1 and m plus 1. So okay, so these are your new configuration. C goes to C prime. For every such transition, you have to find a C double prime. Okay, I will give you that, right? I mean, because here, I mean, let me give you that, okay? And we'll try whether it works, okay? So now, what I do is that this is just this. How can you construct this configuration? What other configuration can come to this one? Can you think of something? K plus 1 n minus 1. Okay, great. You already can. So K plus 1 n minus 1. Okay. Okay. So if, and then this is M, okay, and then whatever, you know, this is the configuration, okay. So now I want to balance, right? I mean, a pair this flux should balance with this one, right? I mean, that's what my check. If I can, and this is a unique one for every time. This is that. This is a new, this configuration is unique, right? I mean, this is true, okay. So you can say that what if n equal to 0. Of course, this transition doesn't happen. Then I don't have to bother if the transition n equal to 0. But then, you know, this is also n equal to -1. So you don't have to bother about that because the transition is not there if n equal to 0 anyway. Okay, so n is greater than 0. So now, so what is the probability of this configuration? I mean, this factor, because the number of particles is same, this factor is same everywhere. We will not write that factor. So this one, the probability, right? I mean, in this probability, Qn and this drops out because they're same everywhere, because I want to make a balanced condition. So this is f of this, f of this, f of this, f of k plus 1, f of n minus 1, f of m, and whatever, rest of them, right? So probability, just f of k plus 1, f of n minus 1, f of m, and others, okay, including these factors. Okay, these factors is whatever, that's some factor, that's the factor, these two factors. Okay, so probability of this, and what is the rate from going from here to here? What is this rate? uk plus 1, because particle is going from, when you go from here to here, I drop this indices, it's not needed. So when you go from here to here, just from particle goes from here, so uk plus 1. So I write here this times uk plus 1. Okay. So this one, probability times rate, that must balance with the second one. Okay, so that is basically, that is same, that has to be same. I do not know whether it is same. This is a check I am doing, right? I mean, you know, this is the check I am doing, right? I mean, if they balance, that's the demand. So this is f of k, f of m, and f of m, and u of n, right? So now you can see that f of m, you know, here and here cancels. All these things which are other factors also cancels, and everything, whatever this dot 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 I written, they are kind of same because they have not changed. So they also cancel. So the one which remains is only that. So equation, and then now in this equation, k here, n here, and k here. So I put also all the k's to the other side. Okay. So let me write it in a different way. So that is, I'm just writing f of k plus 1. U of k plus 1 divided by f of k equal to f of n, f of n, u of n divided by f of n minus 1. Okay. But now look at this structure. So this is this, if you know, this is demand. I mean, this equal to is still a demand. I mean, you know. So we want it to be true. If it's true, then we can find f. So now question that, can you consistently find f from these equations? Then you know we are done. Then these answers could work for us. Okay. So now what we do is that you look at this function. It is just a function of k, right? I mean, you know. So if I call it gk, some gk, what is the right hand side? gn minus 1. But n and k can be any numbers, right? I mean, the number of particles in some sides, right? I mean, they can be any number. So that means that g, if you put 1 here, 2, whatever you put, that has to be right, right? So what kind of function g must be? Constant. So this has to be constant, okay? Some constant c. So now, now you can find here, right? So this tells me, now I will erase this, you know, you can probably find this solution. So fn equal to fn minus c, fn minus 1 divided by un. Okay. Okay. So now can you? So you can iterate this function, right? Now you can iterate it many times, right? I mean, because fn minus 1 you can use this same function. Okay. So can you tell me if you do it next step? So this is c again, fn minus 1. I have to write c square, fn minus 2, like that, right? I mean, no. So finally, if I c square, okay, let's write one more step, n minus 2 divided by u n minus 1, right? or un minus 1. Okay, un minus 1, un minus 1. Okay. So now if you do it, if you repeat it, can you tell me the final answer? So now I'm not using any more because I can see that I can get answer. So this question marks I'm taking it away, and it looks like the answers works, and we have a solution like that. So we write that now. So now what we have is that f of n is directly related to the dynamics. So this is c to the power n, okay, and so 1 divided by uk, product over I equal to 1 to k, product k equal to 1 to n, all the products un minus 1 up to u1, and then f0. So this times f0. Okay, so this is my fn. So let us keep it, and this is true for any n. So for any u. So if you choose, if you have a u, we get a steady state like this. Calculations are not done, but we have a solution, right? So if you have a rate, you get a fn in terms of the rate. So it is, in principle, it is being done, it's solved. Okay. So now let us say that how to take care of this conservation, because this is the part which will bother us anyway, because and our task is to find rho z, right? And try to go to a different ensemble firstly, because because this qn is not something which you can anyway do this sum, and we go to the different ensemble and try to calculate this rho z, and that's all we do today. Okay. Okay. Any questions until now? No. So these numbers are there. We'll see. Like anyway, fn will come in the probability, right? There is a normalization factor, so it will not bother us, because any observable, whatever you measure, it will be just product of something. So let us, we'll go a little further. We see that it will not matter. So you also do not know what this constant is, right? That will also not matter. Okay. So we'll see how. Okay. So now let us write qn. So qn is just the sum of that, right? Sum of this term. So qn is just this sum over all configurations. So qn, and that's the way it has to be normalized. That's the way I could write 1 here. So this is summation over all ni. Okay, and there is this term product over I equal to 1 to L f of ni. This is term, and then there is other term which is delta of summation over I ni minus n. Okay, this is my qn. Okay, and this n1 means n1 equal to 0 to infinity, n2 equal to 0 to infinity, like all the n. Okay, so this is all configurations. So this is we start. Okay, so now what we want to do is that we write a generating function for this qn. Okay, so the generating function this is that the way we do that, like you put z to the power n, summation over n equal to 0 to infinity. Okay, so we also put a sum n equal to 0 to infinity and z to the power n. Somewhere let's put it here, z to the power n. Okay. So once you do that, what will happen is that this n sum you can do immediately, because n was here and this n is here, right? With delta function, if you make a sum, n will replace by summation over ni, wherever n is there, right? So basically this equal to immediately summation over ni, all ni, z to the power n will be replaced by summation over I ni, that's z to the power ni, times f of ni. Okay, f of ni product over I. Okay, the delta function is gone. Okay, so product over f of ni basically means that let us look at this. Z to the power ni means z to the power n1. Okay, z to the power n1, z to the power n2, z to the power n3, and from here f of n1, f of n2, f of n3. Right. So if you write only terms which are n1, only terms which are n2, so this will be just this equal to summation over n1, n2 like that, and n1, z to the power n1, f of n1, and then other terms also are the similar terms. Okay, z to the power n2 sum of n2 and n1 sum now can be done, right? I mean, you know, so now you just say that summation over n1, okay, and this is this times z to the power n2 summation over n2 f of n2, but there these are dummy index n2 equal to 0 to infinity. There is no restriction anymore, right? So this is just z to the power n fn sum, whatever the sum. It will be a function of z, n will not be there, right? I mean, its sum is 0 to n equal to 0 to infinity. Okay, so this equal to fz, I call it some function f, whatever this function I call f, fz whole to the power l. Okay, so now I just say that if I call it my partition function, this is gz. I mean, you know, there is a general name capital Z, also equivalent to the grand partition function capital Z. You can call it that. This Z is just fz to the power L. So this one turns out to be fz to the power L, where fz equal to fn z to the power n summation over n equal to 0 to infinity. That's the result, right? This z we find. So we don't go to calculate like, you know, fz, find the coefficient. I mean, you know, that I don't repeat, right? I mean, you know, of course, if you take fz, you try to find out coefficient of z to the power capital N, whatever, 30, then you will get part q30. Q30 is thus expand this, get the coefficient of z to the power 30. But that is a useless exercise, right? I mean, you know, if you need it, you do it. But I mean, just saying that, you know, there is another interpretation. We go to the, we work using this as if, you know, Z fixes the density, like temperature fixes the average energy. Or chemical potential, here chemical potential fix the number of particles. So I'll erase that. Okay. So now, so let us calculate what is this. Okay, because Fn you know. Well, before calculating, let us do little, you know, let us specifying what is u. Let us go a little further. Okay, so is it z is f to the power L. Okay, so if I take log z, which is free energy, so that will be L log fz. Okay, so then you can see that it's proportional to length. Okay, so the free energy has to be proportional to the volume, I mean, that you are getting. So it's a correct, and you know, each term this fz is coming from only one side. Okay, so this ensemble is pretty simple, and everything is just uncorrelated. It's just whatever you get at one side, it's just that. Okay, free energy like quantity. Yeah. Okay, yeah, because, you know, as I started there, it's a non-equilibrium system. It's a similar thing where, you know, free energy like functions you are getting, but you cannot say that it's exactly, you know, the same free energy what you get in equilibrium. Okay. Okay. So now let us say that you want to calculate n average. That's the first thing, right? I mean, no, because this calculation is not complete, because if you want to describe a fixed n ensemble, you need to know what z should be used, right? I mean, no, you have to know what z you must use, and that, right? I mean, this is not complete. Grand partition function, this is not complete without specifying how rho z changes with z, right? I mean, you have to know that. So now, given this as a partition function, now you can see this is equal to that. So now, as I say here, if gz equal to this, you know that this divided by gz is a probability, right? I mean, no. So probability now in this ensemble, the probability of a configuration ni. So that is just z to the power n. N is summation over ni, right? And qn divided by z. Okay, so that's your probability of having this, right? I mean, in this ensemble, this z to the power n, because this sum is again 1. If you divided this here, and of course this is 1, right? I mean, you know, each of them can be, so probability of this. So z to the power n this. So now, if you want to calculate n average, so you just multiply it by n here, and sum it up. Okay. So what you have is that n average, for that matter, any observable average. So right, generally any observable average. So that will be O and z to the power n qn summation over. Of course, O depends on all configurations. It need not be on n. So this is n divided by z. Okay, and then but in a specific case, we are bothered about n. So we put it n. Okay, n average equal to n z to the power n qn. So now, if you let us say that if you know z, can you relate this n average with z? Right? I mean, you look at this expression. So z to the power. So let us write that. So let us write this equation. So right, I mean, you know. So your so your z, you want n z to the power n. So now your this one, the partition function is just z to the power n qn, that was there. Okay. So now if you just differentiate with z, d by dz, then this n comes here and there will one, this will be n minus 1, but then you multiply by a z also, then this will also go away, right. Z d by dz of this is just n this. Is it clear? Right, I mean, you just differentiate it to multiply. So every time you multiply z d by dz, you pull out one n. Okay. So z d by dz, so this is, you know, pulls out one n, pulls one n, pulls n. Okay. So if you want n square, you just put z d by dz, z d by dz. Okay. And then there is a, you know, there is a z below. Okay. So your n average, so basically n average, if you look at here, this one is z d by dz of this one, and then there is this partition function. Actually, for partition function, let me use gz. I mean, you know, probably because this small z, capital Z should not confuse. So I will change the notation. This is gz. Okay. This is my generating function. So what I write is that this is also my generating function gz. Okay. I'm going out. No, this is my, now I change the notation a little bit. I think that is just to avoid the confusion. My small z, capital Z looks sometimes same. So what I do is that, so this one is z del by del z. So n average equal to z d by dz of gz. Okay, this is the partition function. But then you have also gz below. Okay, and you know, a very, because this kind of differentiation z d by dz comes all the time, it is good to say z is e to the power mu or something. Okay, so that z d by dz is just d by d mu. Okay, so you know, you can have a different, z can be written as e to the power mu. I mean, you know, so that's the same equation, right? I mean, you know, z as mu is the same, you know, they're equivalent. Okay, so if you make this, so then check that z d by dz is equivalent to d by d mu. Okay. So this is just a simpler notation, notationally simpler. Okay. So I will use just z d by dz of this, but then z d by dz of this, so this can be written as z d by dz of log of gz. Okay. But log of gz is just fz to the power l. So this is l log of fz. Okay. This gz is just fz whole to the power l. Okay. So I put it here. So this is same as z d by dz of fz to the power l, but l comes here. Log of fl. Okay. So n average by l is density. So you can write like that, or you can write also z f prime z. Okay, no, okay, it's fine. Okay, so this is the equation. So you can take this L to this side and let us write the equation for density. Okay, so I need one equation, this equation for density. So rho, which is a function of z now, this equation, this is just, this is, there is a z here. Okay, and then, you know, if you log fz is just 1 by fz also, you can say, right? I mean, you know, 1 by fz d by dz of this. So it's a simple expression is that z f prime z divided by fz. F prime is the derivative of that. Okay, so that's the definition. That's the calculation. Okay, z f prime z by fz. Okay, so now look at fz. Fz is actually as if fz is a partition function for a single site. Okay, so it's the calculation becomes simpler because it's just, you know, this is a product, and just because it's a product, and you know, because this restriction you have taken away, it just becomes independent product, right? I mean a completely independent one. So this is just a partition function of 1n. L naturally comes out. So this is this the density. Okay?
So the zero range is showing up there. The fact that the interaction is zero.
Yeah, the zero range, yeah. So Samik's point is that just because you talked of zero range process, it's not talking to the neighbors, and that except that there is a conservation, and once you take away that conservation, you know that zero range is coming here because it's just becoming a product measure. Okay. So fz equal to z f prime z, but the reverse is not true. There can be a situation where particles actually interact or in the one range, but then it's still you can have a factorized steady state. Okay, so that can be true. For example, I mean people who know misanthrope process and things like that. Okay, so rho z equal to that. So now all we wanted to know that do you know can now the solution is there for all you. You can calculate whatever you want to calculate, but we try to take a function for which actually this rho z goes to 1 become finite. Okay, let us do that calculation. Okay, some rate we want to transfer rate is such a function that this one becomes finite. Okay, in that case we will have a condensation. So that's what we will do. I don't want to erase the other side, so this one I will erase. Okay, so so this is a case which is a solvable case. Okay, I try an example which actually takes Ornov's these functions into account. So the same zeta function or something. So that's what I want to get. So let us take un equal to n divided by n plus 1 to the power alpha. Okay, some function I take. Okay, so I mean for which I have a simpler calculation, and I know I want what I want. Okay, so what is so this is if n increases, right? I mean for this is a decreasing function. If n goes to infinity, this becomes 1. Okay, a decreasing function. If you remember in the first lecture, which I said that if it is decreasing to 0, then you have condensation all the time. If it is increasing, you don't have a condensation. So a decreasing function going to a constant is a desirable thing. Okay, so this is a function I'm choosing, a decreasing function which goes to a constant. Okay, so that's the choice. Okay, so now if you take that, can you tell me what is fn? I mean you know why I choose this function, because you can easily say what is fn. C to the power n f0, that is there. Okay, so these terms anyway they are hanging, let us keep it here, c to the power n. Okay, so let it be there. So what is this term? 1 by n plus 1 to the power alpha, right? Because this is 1 by 2 times 2 by 3 times 4. This alpha you can put later, right? 1 by 2, 2 by 3. The last term will just read, and first one and the last one, everything else cancel. So that's the way I choose this function, right? It has this property and it is simple. So fn is 1 by n plus 1 to the power alpha. Okay. So now, and of course f0, if you allow me, because anyway there is the normalization of these functions is taken care by gz. F0 can be set to 1 without any difficulty, right? I mean, so f0 can be dropped to 1. Huh?
It's 1 by the product of u.
Oh, then I think
In the denominators.
I take I take the other one. No, I want this. Fn is 1 by n plus 1 to the power alpha.
Then it's increasing and saturating.
It increasing saturate, yeah.
Then it will not keep on. It should decrease and saturate. You put 1 plus 1 by n to the power alpha.
No, this is still okay. This is still okay. 1 by n to the is it giving me 1 by n plus to the power? So this is 1 plus 1 by n whole to the power alpha. This is 1 by alpha by n. The same thing. Okay. So I just change it a little bit. Okay. So sorry, this was a mistake. No, I don't have a note there. Yeah. Okay. Anyway, so un equal to n plus 1 by n. So this is 1 plus 1 by n whole to the power alpha. Okay. So fn is 1 by this. No, I'll tell you. So if it is increasing one, it will not happen, right? If it is, so let us say in the what was wrong with the other situations. Fn is n plus 1 to the power alpha. Okay. So in that case, you cannot expect condensation because it's kind of larger. You don't expect. Okay. So you wanted this to be a decaying function fast, like larger one. So Fn is 1 plus n to the power alpha. So now so f0 I can drop, but then I have c to the power n remains. Okay, let it keep, because there is n here, so I'm not sure, I'll keeping it. This c still I do not know. So now can I calculate fz? What is here, fz here, fz is just fnz to the power n. So fz equal to just zc whole to the power n divided by n plus 1 whole to the power alpha and summation over n equal to 0 to infinity. Okay. So this one, now you can see that c doesn't appears only along with z, right? So just because z, you are looking for a radius of convergence of z, you can effectively you can say that just zc, right? Zc equal to your new z, because right, so zc is your new z, because you want to set this z equal to 1. Your radius of convergence is z equal to 1, right? So if it's a function of zc equal to 1 will give you new radius of convergence. So z equal to 1 by c now. You don't want that kind of, just rescale this variable. So I can drop now c, right? This is zc is, this is a function of zc. Instead of writing fz, I can call it f tilde of zc, and zc I can call it new z prime. So f tilde z prime equal to z prime to the power n. So it's the same function. Okay, you agree? Okay. So fz I drop c, z to the power n divided by n to the power alpha. So now let us do 1 plus 1 and 1 by z. Okay. So now n equal to 0 basically means that it will start with 1, right? If you start with n equal to 0, so I can start with, this is z to the power n plus n divided by n to the power alpha summation over n equal to 1 to infinity and 1 by z. Okay. This just the first term. I just read the sum. And this function, do you remember? Li function, n equal to 1, it is z equal to 1, it is a zeta function. So this is this function which Ornov defined there. So this function is just 1 by z g alpha, but I am using g there. Anyway, no, zeta is very complicated. I cannot. My hand doesn't work. G alpha of z. Okay. G alpha of z. Okay. So now all I want is, it's not enough. I also want f prime z. Okay, but of course anyway at the end I have to take n equal to 1. But can you tell me now what will be f prime z? Right? What is f prime z? F prime z is just, we have to differentiate with z. So this becomes n plus 1 here, that cancels with 1, alpha minus 1, right? 1. So let us calculate this. F prime z equal to z to the power n divided by n plus 1 to the power alpha minus 1, because this n plus 1 comes here, cancels with this one, alpha minus 1, and summation over n equal to 0 to infinity. Okay. So this one can again be written as, this is plus 1 by z, and this is g alpha minus 1 of z, 1 by z, 1 by z g alpha minus 1 z. Okay. Oh, so there is another term. Okay. So minus 1 by z square, 1 by z this, minus 1 by z square times g alpha z. Okay. Done. Okay. So now you calculate this one. What is rho z then? So what did I? This is z square. 1 by z square g alpha z, 1 by z this. So so can somebody help me? So 1 by z we just cancel out, because we have f z f prime z. So z f prime z equal to g alpha minus 1 z minus 1 by z g alpha z z f prime z divided by gz is 1 by z g alpha z. Okay. So this z goes up, so this is z and this is minus. Okay. So rho z is just this, and all we want is that rho z goes to 1. Okay. So these are the same functions, and so if you take limit z goes to 1, so this z goes away, and all these g functions becomes Riemann zeta functions now. Okay. Because if you put z equal to 1, 1 by n to the power alpha, that's a zeta function. Okay. So this is zeta rho z. So this equal to z goes to 1, zeta and zeta alpha minus 1 minus zeta alpha. You see why I was not using zeta alpha divided by zeta alpha. Okay. So zeta alpha, so this minus 1. Okay. So zeta alpha minus 1 divided two different notation I am using. So zeta alpha divided by 1. Okay. So this is true only when, right, if you know zeta functions, this is true only when alpha is less than 2. Okay. Otherwise it's infinity, because this sum, look at this sum. Okay. So this sum, if it is 1, this sum is like an integral, right? So the density, so if it is greater than 2, it is converse. It converse. If it is it converse. Okay. If it is less than 2, then it's a problem. Okay. No, I'm. Alpha equal to 1 certainly diverges. Yeah, alpha equal to 2 also, right? So less than 2. Alpha has to be less than 2. Can you do you remember this numbers now? So okay.
I have realized that at 6 p.m. I cannot think.
So basically this one. So okay.
1 plus 1 by into the alpha. So you need the condensation if alpha is less than equal to 1.
Yeah. No, alpha is less than 2. Here it is 2 because it's 1 plus b by n b. No, because this is 1 plus n by n. So this u equal to 1 plus, right? 1 plus 1 by n whole to the power alpha. To the first approximation, this is just 1 plus alpha by n. So alpha less than 2, there is condensation. So for if alpha less than 2, you will have it finite. Okay. Because n goes to infinity is not the point, and there is also finite sum here. Okay. So this equal to, so this function, if it is if nu or whatever alpha less than 2, this is just this one. So this is zeta of alpha minus 1 divided by zeta of alpha minus 1, and if it is greater than 2, then this is infinity. Okay. So that's the result. So basically what you have, if you choose a function and this is, let us say, 3 by 2, alpha equal to 3 by 2, then you have this and this one is just what you call rho star. Okay. So then you have a scenario like that. Okay. So rho star is finite. Okay. So basically what you have is that you have a macroscopic condensate at some place. So okay. So this situation is, so the situation is similar to what we know as Bose-Einstein condensation, but the difference here is that so the Bose-Einstein condensation was in a momentum space. Okay. So it is not that when you want to put particles, it is not that only particles are there. You have also another thing to take care of, right? You want to put particles such that the energy is also minimized. Okay. And then in the K space there are energy levels, and there is one which is lower, next something, it's ordered, some ordering is there. Okay. So if you want to put your condensate, where should you put so that you have the lowest energy? It's just here. Okay. Because the sites are has some identity, and the lowest one is the one where you put it. That's the Bose-Einstein condensation in K space. So in this particular case, all sites are equivalent. Okay, so the condensate can occur anywhere. That's the point. So now you might ask a question. Let us say, because it is zero range process, you can say that at each site you have a different rate. U1 at first site it is U1, second site it is U2, third site. These are different functions. Each of them is some functions like that, but maybe alpha is little different. Let us say alpha is some number which is little different, and the functions are different. So now question is that in this way, if the sites are with different rates, then there is one rate which is slower, right? Then slowest. The one which is slowest is the one where the condensate will go and sit, like Bose-Einstein condensation. Actually, if you do the calculations, you directly can show that the function, that everything just fits like a Bose-Einstein condensation. So there is a good reference on this zero range process in archive. I have the reference, but I think Martin Evans, by Evans, yeah. So I don't. It's by Martin Evans, M. Evans, and Henny, yeah. Henny and Evans, and this is archive. I don't remember the number. 2005 review article. This is review. J Physics A, in the published J Physics A, but it is also available in archive. J Physics A 2005. Okay, so I have the reference, but I have to look for it, and my hands are dirty, so I don't want to touch my mobile now. No, it's okay. Oh, it's recording. Okay. Yeah, okay.
No, I just wanted to say, pairwise balance, you discussed very well. It may give the impression that it is valid only in one-dimensional systems. It's valid in any dimension. I just wanted to say this.
Yeah. Yes. So other thing is, one other thing which I just wanted to point out. So while constructing these functions, like I have a function which is here, and Samik said something, I just put expand and I say something like that. Okay. So this you can also prove. So now you can you have z f prime z by fz. Okay. So instead of this, you don't have to assume any un. Okay. So the calculations are simple. You put whatever u, just continue with this u, and then come to this point. Okay. And you can show that how un should behave. Okay. So the general result here is that if you do that, just take these expressions, put it here, and all you want is that this density z goes to 1 is constant. So for that, un should have certain property. Okay. So that property I will just state, but I will I will leave it as exercise. So the property is un, right? Not equal to, right? Not proportional to, let us say. Proportional to, okay. Okay, 1 plus, so any function un, okay. So you take a function un, you expand it around n equal to infinity. So n equal to infinity, this is going to a constant. So there is a constant term, some constant term u infinity, okay, times 1 plus, if you are expanding around n equal to infinity, the first term is some b by n plus c by n square plus, right, some other terms, okay, some function, okay. So the demand, I'm just saying, the demand is that you have a condensation transition only when b less than 2, okay. So condensation transition for b less than 2.
And the other things?
Nothing. All these coefficients, it doesn't matter what you put. Okay. So this can be shown. So that how do you show that? Is basically these are kind of series, right? You have to convert. You have to look for the convergence of the series. You just take a ratio test. Okay. So if you take the ratio test, you can check that the ratio goes to 1, but then when the ratio of terms goes to 1, you have a different test, what is called Rabi test or something. So Rabi, okay, so that so that's basically 1 plus 1 by n. It should be slower than 1 by n. Okay, 1 plus 1 by n. So then it will have a convergence. So that's the statement. So if any function un, you can expand and you can see if b is less than 2, then it will happen. So it is the other scenario is that, okay, I think I'll continue for, I'm not done, na? 5 minutes is there, so I'll just utilize that. So now, question that when will the condensation occur? Just one. It's okay? Show me. No, I just 1 minute, I'll just send. So now question is that, you have a density and you have a B, right? I will also draw a phase diagram like Arnav has drawn. So basically, you know that B, okay, maybe later.
I have nightmares about this now.
Okay.
No, I'm kidding. Let's.
So rho C equal to 1 by B minus 2. Okay. So if you take, so this is the general situation. Okay. So you can write, you can say that, so take a very specific case. You say that, let us say that a situation when U actually, this is 1 plus b by n, that's the result, that's the one, that's a new function. Okay. In this function, if b is less than 2, of course you have condensation, and this is also solvable. But when you say what is rho star, in this case what is rho star, in this case I find what is rho star. Okay. So I put rho star as a function of b. Okay. So so b equal to 2, below that there is no, above that there is no condensation, right? This side is non-condensate. So now here there is a condensate, but condensation for density above certain thing, right? Here, if you are above this, then you have condensation, right? That's the point. So in this one, I have a function this, zeta, the numbers as a function of alpha, I don't remember, I cannot plot. In this situation, if the function is this, rho C is just 1 by b minus 2, okay? So you can b equal to,
condensation will be possible if b is larger than 2.
did I, this one is b is larger than 2? Yeah, b is larger, b greater than 2. Okay. So now 1 by b minus 2 it goes like that. Okay. At 2 it diverges. Okay. So this is any b. So this is the side you have no condensate. B less than 2 there is no condensate. So this side is no condensate, and this side you have condensate. So even if b is here, if you are at this density, you don't have a condensate. So for a given model, it's not that for any density you get a condensate. Your control parameter is now density. You increase the density above this side you have a condensate. Okay. So that's the condensation transition. Okay. So I think that's where I stop. Okay. It people are tired.